Data here. So today I wanted to create a linear model and also a maximizing function to look at the relationship of revenue and price. Now, all credit on this video to a very smart friend of mine named Stefan, who really taught me all of these methods. And if there's anything I added to what he said, it's really only in translating what he said into our code. So I'll write up a Medium article about this method with the code sharing like I do, and I'll link his profile. So credit to him. So anyway, relationship of sales to profit. This will kind of be an intersection of the other videos doing linear models, but also some of the calculus that we could explore in a programming environment also. So the first thing I'm doing here is I'm creating a variable called start date and another variable called end date, and then I'm using the seq function and specifying the from and to arguments as being from the start date to the end date by day, which gives me a vector of 365. And then I'm creating a new variable called brand, which is Toyota. And I chose Toyota just to kind of be on theme because everything else I'm doing is empty cars, but it could be widgets, it could be couches, it could be anything. So that's also 365 all the way down. And I'm creating the price of these Toyotas as having an average of 100 and a standard deviation of 10. Now, I guess a Toyota doesn't cost 100, maybe 100 represents something else, but I'm making the math easy by choosing 100, so ignore that. And then finally what I'm going to do is create a data frame of these different vectors using the data.frame argument. And then I write an extra open parenthesis and an extra closing parenthesis at the beginning and end, because that way it creates the object, but also will print it in the console. It'll also print it in the console in the R markdown in between the backticks. So here I have a data frame of 3 columns, one for each day, and it's telling me the price of the Toyota on different days that I sold it. So let's say hypothetically that the price keeps switching around from one day to the other. Now I'm also going to create another column in this data frame, which is the quantity sold. And here I'm arbitrarily creating that quantity sold as being a perfect linear function of the price. I'm specifying, just like a linear model, the beta 0 intercept and also a beta 1 coefficient of 0.5. And here I have quantity sold. And what this is doing is it's ensuring that when the price is high on this product, I'm selling a lower amount, and when the price is low, I'm selling a higher amount. Hence the minus sign in the equation. Now, if I copy and paste this ggplot up here, and run this code, you'll see a perfectly straight line with a correlation coefficient of 1. So it's a perfect linear function. But like in real life, the sales data doesn't turn out that way because the price is not the only thing affecting sales. It could be the weather, it could be competitor activity, it could be anything. So I'm going to change this quantity column by adding the result of something from the RNorm function, which is the random normal distribution, and I'm specifying a standard deviation of 5 in order to add variability in that linear function. So now when I run the same line of code, you'll see that the dots are scattered around, and this probably more resembles what you might have in sales data. Now if I took that data frame and I created a new column called revenue equaling price times the quantity sold, and I arranged it descending by revenue, it wouldn't necessarily be obvious what the optimal price of the product, the Toyota, should be in order to increase revenue, because sometimes that price is $115, sometimes it's $109, sometimes it's $98, and on these days the revenue is high. But what you're really seeing here is that variability that we baked in by specifying a standard deviation of 5. So let's create a linear model. The linear model is of the form quantity as a function of price using our data frame. We do that with the LM function in base R. And then the natural output of that linear model is going to give me these two different values for the coefficients. One is for the intercept and the other is for the slope. Now in a linear model with only one y variable and one x variable, the slope is going to equal the person correlation R multiplied by the quotient of the standard deviation of y over the standard deviation of x, and the intercept is going to be equal to the mean of y rather, which I can call y bar, multiplied by the slope. Actually, y bar is subtracted from the slope multiplied by x bar. So that's one way of finding the slope and intercept of that line. Okay, so to return a little bit to algebra here, if I take x and I multiply it by 1 minus x, that's the same thing as saying x, or 1x, minus x squared. And that's true as long as x isn't equal to 0 or x isn't equal to 1, because then you're multiplying by 0. So up here, I specified revenue as being equal to price times quantity. So here revenue equals price times quantity. But I can also change quantity to be the result of our linear model up here. Now our linear model, we know, has that beta 0 term plus the beta 1 times price. And distributing this algebra the same way, I can actually type revenue as being equal to beta 0 times price plus that beta 1 coefficient times price squared. And now I have an equation for revenue that doesn't talk about quantity sold. It only talks about price as being a squared term. So here I have revenue equals price times quantity, but I'm going to create a different thing that's called revenue model that has that averaging built in from the linear model. And I'm going to specify, I need to redo this beta 0 and beta 1 term because I ran it once already in prepping for this video. Right, so I can comment these out because these are all different ways of just writing the same equation. Instead of specifying revenue and typing it, I chose the coefficient of the model at the first term and the coefficient of the model at the second term. And here, revenue model 3, I'm doing the work of distributing it, so I'm only writing it in terms of price as a squared term. But here I have the same value even after I distributed it, revenue model 2 and revenue model 3. And now, if I were to graph this, car sales, you would see a parabola, or an inverse parabola. There we go. Now, the idea here is that the point at the top of the parabola, where the derivative, where the slope of the line is 0, is going to be the price that maximizes revenue. So I can eyeball that by adding geom h line and an h line with a y-intercept. This slope is 0. I overshot it just a tad. But also I can work this out in the math. So my beta 0 term is 101. And my price term, my beta 1 term, is negative 0.5. So here's R as my squared term for price. And in order to get that derivative, I multiply negative 0.5 by 2. And I'll just take this term right here. So this is the derivative of revenue. And then I am going to put this onto the left-hand side of the equation, and I'm going to divide by this number because I'm setting the derivative to 0. A derivative of a parabola is going to reflect the minimum or the maximum. And when I print this out, it should equal 98.6. And that's the value on the x-axis where the parabola is highest. So it should be the theoretical price at which the revenue would be maximized. All right, like and subscribe if this is helpful. All credit to my friend Stefan.